Welcome back, everybody. This is our second session in JEE mains previous year questions for chapter Dual Nature of Matter and Radiation. Before this one, we have made one video in this series, and that video is available on our channel's playlist section. If you have not watched it, then you can go to channel's playlist section and watch those videos. We have also started similar series for NEET, and all those related videos are live in the NEET playlist, so you can also watch them for additional practice. And if you find them useful, then do press the like button, share them, and subscribe to our channel. With this, let's start today's video. In the previous one, we covered up to question number 10, I think. Yeah, I think this was the last one, last question. Let me adjust pen thickness. And today we will start with question number 11. If the de Broglie wavelength of electron is equal to 10 raised to power minus 3 times the wavelength of photon of frequency, this hertz, the speed of the electron will be equal to. So we know that de Broglie wavelength for electron will be equal to h by momentum, and wavelength for a photon will be equal to, we know that energy is equal to hc by lambda. So lambda will be hc by E, and it has to be written in terms of frequency. So we can write hc by energy can be written as h times frequency. So basically we know the relation, that is we already know, that is c by frequency. So the ratio is given, then speed we have to find out. So lambda E can be written as h by mv, and lambda for photon is c by v. Sorry, c by nu, where nu is the frequency of the photon. Now if I divide both of these, so for electron divided by photon, that is equal to 10 raised to power minus 3. So this will give us h by mv into frequency by c is equal to 10 raised to power minus 3. Now from this we can calculate velocity. So from this, velocity will be equal to h nu by mc into 10 raised to the power minus 3 is equal to velocity, or v. So h is 6.63 10 raised to the power minus 34, frequency 6 into 10 raised to the power 14, mass 9.11 10 raised to the power minus 31, and c is 3 into 10 raised to the power 8. So this will get cancelled on 2. Now what we will get? Now multiplying 6.63 by 2, we will get approximately 13, and here we have divided by 9. I am approximating it. So this will be 13 by 9 into 10 raised to power minus 34 plus 14. This will give us minus 20. And in the denominator, from the denominator, we will get plus 31 and minus of 8. So this will, on solving, we will get 1 point. That will be approximately 1.5 approximately, I think, into 10 raised to power minus 28 plus 3, that will give us 6. Oh sorry, minus 3 plus 3 it will give us, and I think I am missing plus 3 somewhere here. Yeah, I forgot this 10 raised to power minus 3 term, so this will be minus 3 here, so this will get plus 3 here, and this will be 1.5 10 raised to power 6. So that matches with option D here. So option D will be the right answer. Moving to the next one. In an electron microscope, the resolution that can be achieved in the order of wavelength of electron to resolve the width 7.5 into 10 to the power minus 12 meter. The minimum electron energy required is. So here, because we need resolution, so to get an resolution, what we need, that lambda required for resolution should be comparable to the width or the size we want to resolve. At least lambda should be comparable to the width. So from this, width is given to this value. So lambda will be equal to 7.5 into 10 raised to the power minus 12. Now this is the lambda for electron, and we know that lambda for electron is h by momentum, and momentum can be written as 2me under root, and from this we can write for energy of an electron that E is equal to, after squaring, h square by 2m times lambda square. So that will be 6.626 10 raised to the power minus 34 square divided by twice m, that is 9.11, and lambda, that is 7.5 10 raised to the power minus 12 square. When we solve this, we will get answer something around 20 kilo electron volt. So that matches with option D. Now some of you might also, I can say, will get confused that this question is basically related to diffraction, and in diffraction can still occur if lambda is comparable to half of the width. Diffraction can still occur, or we can say we can still resolve within the diffraction limit if lambda is comparable to half of the width. Now if we take half of the width, or we can say w by 2, lambda as w by 2, then what will happen here? From this, what we will get, that here we will get divide by 2 and whole square, and from that our answer will be 100 kilo electron volt. But from that energy is increased, and what we have to find? We have to find minimum energy required. So normally for diffraction, what we take case that lambda is comparable to half of the width, but here we will take comparable to the width because we need minimum energy required. We can say for resolving, we can take any value between width, half of the width, to proper width or the complete width. So here that's why we have taken lambda is equal to width. True electrons are moving with non-relativistic speed particular to each other. Is corresponding wavelength are lambda 1 and lambda 2. They are de Broglie wavelength in the frame reference attached to their center of mass. Now, as they are moving perpendicular to each other, then we can assume that V1 is equal to, and their velocity is also not known to us because velocity is not mentioned, either it is equal or not. So let's say first one is moving in x direction and second moving is in the positive y direction with velocity v1 and v2. So lambda 1 will be h by m1 v1 and lambda 2 will be h by m2 v2. And here we have to find out, we can say, de Broglie wavelength in the frame reference attached to center of mass. So here velocity of the center of mass will be, that will be the total momentum, that will be m1 v1 plus m1 v1 I plus m2 v2 j divided by m1 plus m2. Now using this relation, value of m1 v1 will be h by lambda 1. So this will become h by lambda 1 of I. Second will become h by lambda 2 of j divided by m1 plus m2. And from this, what we can write? We can write that m1 plus m2 into vcm is equal to h by lambda 1 of I plus h by lambda 2 of j. Now what does this term denotes? This term denotes momentum in center of mass frame. This is the momentum in center of mass frame. So wavelength in center of mass frame will be lambda cm will be h by momentum in center of mass frame, and that is given by this relation. So this will be h by m1 plus m2 into vcm, and now this term will be equal to this one, and here as we have vector form, so what we will take? We will take magnitude, and let me write it, that pcm magnitude, and this term is pcm. This term is pcm. So its magnitude will be h outside, and here we will get 1 by lambda 1 square in under root plus 1 by lambda 2 square. So this will become h by PCM whole will be equal to h by 1 by lambda 1 square plus lambda 2 square. Now h gets cancelled, and we can further write, I can if I square and I will get lambda cm square is equal to 1 by lambda 1 square plus 1 by lambda 2 square. Now if I take inverse, then I can write then 1 by lambda cm square is equal to 1 by lambda 1 square plus 1 by lambda 2 square. And this can be written as further, if I want to find the value of lambda cm, then I can solve it like this, that 1 by lambda cm square will be equal to lambda 2 square plus lambda 1 square divided by lambda 1 square lambda 2 square, and from this lambda cm will be equal to lambda 1 lambda 2 divided by under root of lambda 1 square and plus lambda 2 square. So lambda cm, that is, here I'm getting lambda 1 lambda 2 into lambda 1 square plus lambda 2 square, means the most possible answer, the most probable answer will be this one. Here in option it is given additional 2, so I don't know how it is going. And one we solved that it was, if it is lambda cm, then it has to be square terms. Only then this can be possible. So I can say most relevant answer will be option C. Now moving ahead, if the de Broglie wavelength associated with proton and alpha particle are equal, the ratio of velocity of proton to alpha particle will be. So again, it is mentioned that for proton is equal to alpha particle. Now, de Broglie wavelength is h by momentum, so it will be mass of proton. Velocity of proton is equal to h by mass of alpha, velocity of alpha. Now, h get cancelled, and we have to find ratio of velocity of proton to alpha. So this will become mp by m alpha will be equal to vp by v alpha. Now mp by m alpha will be equal to 1 by 4. So that is option A for us. Oh, sorry, I made a mistake. It will be m alpha by mp. M alpha by mp. And that will be equal to 4 by 1. So not option A. Option C will be the right answer. In the next one, a particle of mass m and initial velocity v collides with particle of mass m by 2 which is at rest. The collision is head-on elastic. The ratio of de Broglie wavelengths lambda a and lambda b after collision. So here we have head-on elastic collision. So basically what we have? We will have momentum conservation here. That will be applied. So let's apply momentum conservation and energy conservation also. That initially we have part mass m moving with velocity v and mass m by 2 moving with velocity 0. They collide. So m1 has after collision velocity v1 and m by 2 has velocity v2 after collision. As it is elastic collision, so the coefficient of restriction will be 1, means v2 by v1 minus v minus divided by v minus 0 will be equal to 1. So from this V2 minus V1 is equal to V, or V2 is equal to V plus V1. Now let's conserve momentum. So from that MV will be equal to MV1 plus M by 2. V2 M gets cancelled and value of V2 we can substitute. So V is equal to V1 plus V plus V1 by 2. So this will become 2V is equal to 2V1 plus V plus V1. So basically V is equal to 3V1, and from this V1 is equal to V by 3, and V2 will be equal to V plus V1, that will be 4V by 3. So now coming to the ratio of the de Broglie wavelength after collision. So after collision, assume it is has a de Broglie wavelength lambda A, it has a de Broglie wavelength lambda B, and lambda is equal to h by momentum. So mv. So from that lambda A by lambda B will be equal to ma va, here mb vb. Now mb is m by 2, velocity is, that is 4v by 3, divided by m, and here we will have v by 3. So v by 3 gets cancelled, m gets cancelled, and this 4 gets cancelled on 2. So the ratio will be 2 ratio 1. That is option D for us. Moving ahead, a parallel beam of electrons traveling in x direction falls on slit with D as shown figure. If after passing through the slit, electrons acquires momentum Py in the y direction for the majority of electron passing through the slit, H is the Planck's constant. So it is mentioned that initially we can see here that initially electrons has momentum in x direction, and after passing through the slit they gain momentum in the y direction. Now, here what we can do, we can simply apply Heisenberg's uncertainty principle. According to that we have delta x into delta p, means we get uncertainty in the position into uncertainty in the momentum. Will their product will be always greater than half of h cut, that is h bar by 2. Now, what is h cut? H cut is basically h by 2 pi. So basically, if we write it for the y direction, so we can write delta y into delta py will be equal to h by, so will be greater than equal to h by 4 pi. So delta y is the we can say uncertainty in the y direction. Now, what is uncertainty in the y direction? That is the slit width here. So that is equal to d. Now, change in momentum in the y direction is initially in y direction we have momentum 0, and after it becomes py. So this will become py dpy, and it has to be greater than h by 4 pi. So if it is greater than dpy is greater than h by 4 pi, then it will also be greater than h. So from that, what we can conclude. Oh, sorry. This second, this cannot be concluded directly. That it is greater than, let's say, h by 4 pi is equal to 1. Let's suppose h by 4 pi is 1 for approximation. Then h will become equal to 4 pi. So if some term is greater than 1, if some term, this term is greater than 1, it is we are not sure whether it will be greater than the 4 pi. So either it can be greater than or it can be equal than, but it will not be less, but it will not be very greater than, that means like this option D. So here all the options are, I can say, uh, very possible, that either it can be less than h, it can be greater than h, or it can be comparable to h. So what we will do, we will go with option C, that in most of the cases what we have comparison cases, so that's why we will go with comparable case. Now let's move to the next one. De Broglie wavelength of electron accelerated by the voltage of 50 volt close to. So we know that De Broglie wavelength is h by p, and that can be written as h by 2me, that is energy basically. And from that energy will be equal to q times v, charge times potential. So it will be h by 2m qv. So lambda will be at 6 into 636 10 raised to power minus 34 divided by under root twice the mass, that is 9.11 10 raised to power minus 31, into charge, that is 1.6 10 raised to power minus 19, and into potential, that is here given as 50 volts. So when we substitute all these values and solve, we will get 1.7 angstrom. That is option C for us. Moving to the next one. For which of the following particles will be the most difficult to experimentally verify de Broglie relationship? Now we know that de Broglie wavelength is h by p, so it will be h by mass into velocity. Now, if lambda is very small, then it will become very difficult to measure. And how lambda can be small? For a velocity, either velocity is very high, either mass is very high. Now, in the given options, nothing is given regarding velocity. So we have electron, alpha, proton, and dust particle, and we know that dust particle is going to the have the highest mass because dust particle is a combination of molecules, or thousands of molecules, and those molecules will surely have mass greater than an alpha particle because alpha particle is heaviest between electron and proton and alpha particle. So we can say for a dust particle, it will be very difficult to measure the de Broglie wavelength. And also, there is another concept that we can accelerate an electron, proton, and alpha particle easily. But dust particle is a neutral molecule. It will be very difficult to accelerate it also to the higher velocities. So we can say its mass will play a crucial role here, that because due to very high mass, it will be very difficult for it to have an measurable value of lambda. So option D will be the right answer. Moving ahead, so electron are accelerated through a potential difference V and proton are accelerated through potential difference of 4V. The de Broglie wavelength are lambda E, lambda P for the electron proton. The ratio of lambda E to lambda P is given by. So here we know that they are accelerated by some potential difference. So what will happen? They will acquire kinetic energy in that potential difference, and that will be equal to charge times the potential. So, and kinetic energy is equal to, we know that momentum is basically equal to 2m times the kinetic energy. So from that we can write that momentum becomes, that will be 2m into q into v. So lambda is basically h by p, that is de Broglie wavelength. And if I write for lambda electron by lambda proton, h will be common, so it will get cancelled out, and here I will get mass of proton into velocity of proton divided by, oh, I can simply write momentum. So I can write momentum for proton divided by momentum of electron. Now here in both of these two, both of these has the same charge. If we talk only discuss regarding the magnitude, and both of 2 is also constant, so the both of these will get cancelled out, and basically we will get mass of proton into potential for a proton, that is 4 divided by mass of electron divided by the potential of electron, that is basically 1. So this will get out of the under root, and this will be 2 under root mp by me, and that is option D for us. In the next one, if the kinetic energy of free electron doubles, its de Broglie wavelength change by the factor. Now, as kinetic energy is doubled, we know that lambda is proportional to 1 by momentum, and that from that we can write lambda is proportional to under root of E. Why? Because momentum is equal to 2me whole under root. So if kinetic energy doubles, then lambda dash will be equal to or proportional to under root 2e. So we have to find out by what factor it changes. So if we divide both of these, lambda dash by lambda will be equal to under root e divided by under root 2e, and this will give us 1 by under root 2. So we can say the new wavelength is 1 by root 2 times of the original wavelength. So option D will be the right answer here. Moving to the next one. Formation of covalent bond in compound exhibits. So as we have seen that when we discuss covalent bonds, you have also discussed in chemistry, I think, when we discuss covalent bonds. So what we make there, we make hybrid orbits, px orbit, py orbit, pz orbit, and s orbit, and d orbits. And when we represent them with the help of wave functions, probabilities. Like s orbit is represented like this, p orbits are represented like this. So these are basically wave function, and if there is a wave function, then it has to be represented by the wave nature of the electron. So option A will be the right answer here. In the next one, a beam of electron of energy E scatters from the target having atomic energy 1 angstrom. The first maximum intensity occurs at theta is equal to 60 degree, then E in electron volt. Now here it is mentioned that we have a scattering effect, or basically we can say here we have a diffraction going on. And if there is a diffraction, then we can say that for diffraction, for the maxima, n lambda will be equal to 2d sine theta. And for the first maxima, n will be 1, so lambda will be equal to 2d sine theta. This is the condition for the diffraction. And this will be also equal to, here we know that lambda is h by p, because this is the wavelength of the wave. For diffraction, what we take? We take wave nature, and that wave will have some wavelength lambda, but that wave nature is of electrons here. So here we will have two type of wavelength, one wavelength due to the wave nature and one wavelength due to the particle nature, and both of them should be same, as we are only discussing regarding the same electrons. Both are that electron is behaving both wave and particle. That's why we can take both wavelengths equal to each other. So from wave nature we will get lambda is 2d sine theta, that is from the diffraction, and from the particle nature we will get lambda is h by p. So if we equate both of these, what we will get 2d sine theta, and we have to calculate energy. So I can write momentum like under root 2 me. So from this, if I calculate value for energy, squaring both of these, I will get 4d sine square theta is equal to h square by 2me. Now, some of them might get confused that, sir, we have never discussed this type of condition in diffraction. So, actually, this is Bragg's crystal diffraction. You might have studied some experiment like this, that there is some crystal and there is light incident on it. Then there is a reflected light and there is a reflect light from the transmission, and these two light interfere, and there is Bragg's diffraction. So for that we have n lambda is equal to 2 sine theta, where n is the order of the diffraction. So here we are taking ns1. So from this we have to calculate energy, and basically energy becomes E becomes h square by 8md square sine square theta. So I think, yeah. Now we need to substitute values. So E will be equal to 6.626 10 raised to power minus 34 square divided by 8 times mass 9.11 10 raised to power minus 31 into, here we have D, that is the spacing, that is angstrom, so 10 raised to power minus 10 square, and sine of 60 square. Now when we solve this, after solving, what we will get? We will get approximately, that is, I have already calculated, so you can calculate separately. That will be 0.803 10 raised to power minus 17 joule. And what we can do, we can convert it in electron volt, so that will be 0.803 10 raised to power minus 17 divided by 1.6 10 raised to power minus 19. So this will basically give us half into 100, so that will be approximately 50 electron volt, and that will be the answer here, 50 electron volt. So with this, let's move to the next one. The surface of a metal is illuminated alternatively with photons 4 and 2.5 electron volt respectively. The ratio of maximum speed of the photon emitted, in this case close to work function of the metal, we have to find out. So we know that maximum speed from the photoelectric effect experiment, half mv square, it will be given by energy minus the work function. So first energy is 4 electron volt minus 5, that is work function. Similarly, second half mv2 square will be equal to 2.5 minus 5. Now if we divide both of these, what we will get? We will get v1 by v2 square is equal to 4 minus 5 divided by 2.5 minus 5. Now the maximum speeds ratio means velocity ratio is equal to 2 here. So what we can substitute it equal to 2. This can substitute as 2. 2 square will be 4. So 4 minus 4 by 5. 2.5 minus 5. Solving we will get 10 minus 4 pi is equal to 4 minus 5. So 6 is equal to 3 5 and 5 will be equal to 2. So work function will be equal to electron volt because we have taken energy in terms of electron. So with this, we end this video here. Hopefully what we have covered till now is helpful to you. Again, if you have any doubts and suggestions, you can put them in comment section. I will try to resolve them. And if you find these videos useful, helpful, then share them. Subscribe to our channel. If you want to donate us or can donate us, then do donate us with scanning the QR code. It helps a lot. And again, thanks for watching. We will meet in next video.